Welcome back, everybody. Um, no, nothing to, I don't have anything coming up to tell you. Other than I finished all grading my part of the exam. For this session, the average was about 87, and the range was about 55 to 100. So it was about average. Anyway, any questions, comments, concerns? We do have this chapter we're in. It seems like this is one chapter that seems like we're in it for a long time because it is a lot of information, and I have to go through a lot of detail to get through it. So there is a question: did anyone get 100? Yes, the range was 100 to 55 with the average of 87. All right. All right, so let me begin with where we left off. Any other questions before we begin? Okay. Give me 2 minutes, please. Okay, I'm back. All right, any questions before I begin? We had ended here on page 19. What we're doing is drawing Lewis structures for molecules, compounds, okay? And from that information, which is based on the valence electrons, we are able to actually come up with a structure for that particular compound, and then a geometry. So a rehash, don't forget, you're going to need the shapes table for this part, plus your periodic table, because if you don't know how many valence electrons each atom has, then you're going to have to look it up on the periodic table. Okay, so the other aspect about this process is that once we calculate, determine how many valence electrons we have, that is the number you got to work with. That is what you create the single bonds or double bonds or triple bonds. Remember, triple bonds is the maximum number of bonds that you can make. There's no quadruple bonds. It's either going to be a single, double, or triple bond. Okay. So how do we begin? Well, point number one, you're always going to be given the central atom. That is the atom that where all the other species, all the other atoms are bonded to. Okay. It can be given to you either by the symbol being underscored, underlined, like we have here, or it will be in bold. Okay. So in this case here, HCN, it's written, carbon is in bold. So carbon is our central atom. But what we do is first identify how many of each atom we have in the compound, and we've got one hydrogen, okay? And then identify how many valence electrons we have for that particular atom, total number of valence electrons. So if you have 10 hydrogens, then obviously you're going to have 10 valence electrons coming from that atom. So we only got one, and the number of valence electrons, which I denote here is VE, valence electrons. Okay, so VE. Okay, so we have one valence electron coming from hydrogen, and we know that because hydrogen is in group of 1A for that table. So one valence electron. Carbon, we got one carbon. Carbon is in group Roman numeral 4A. So that tells us we got 4 valence electrons coming from carbon. Okay. And then nitrogen, we got one nitrogen. And nitrogen is in group 5A, V Roman numeral 5A. Okay. So we got a total of 5 electrons for one nitrogen. So the grand total is 10 valence electrons, 10 valence electrons, and this is the number you got to work with, okay? So what I do is I divide that by 2 because we're going to make bonds, and every bond represents 2 electrons, so we end up with pairs. And so dividing by 2, so that number that you get here should always be divisible by 2. So we have 5 pair to work with, okay? Whether you work with the 10 individual valence electrons or 5 pairs, your choice. I prefer to use the pairs. All right, so now that is the number we need to work with. We have to use them all up. And if you need more, you just cannot magically just, add more valence electrons as you need, because the number of valence electrons is determined by the atoms that are associated with the particular compound, okay? And that's your number. It's etched in stone. All right, so carbon is a central atom, so I can very quickly draw carbon, and then here's my line. I get a pair, that's why I prefer lines, and I can attach nitrogen to that. Then I make another one on the other side and attach hydrogen to that. So here with my 2 lines, each representing a pair. So I got 2 pairs that I've used up. So I can subtract, got my inventory going here. I can subtract 2 from the 5 pair that I've calculated with respect to valence electrons. So I've got 3 pair to work with. I got to put them someplace. Point number 1, hydrogen, always put this in long-term memory, only has 1 bond, 1 pair of electrons around, and that fulfills its duet rule, okay? So you will never see, or you should not ever put more than 1 bond on hydrogen. So hydrogen is good. So we can't put any more electrons around it, so we got to leave that alone. We still got to deal with the 3 pair. Now, in my particular case, I prefer to work with the atoms on the outside, away from the central atom, put them on them, and then bring it into the center as needed. Okay, that's just my own personal preference. Doesn't mean you have to do it. Regardless, you got the 3 pair left over, put them wherever you want to put them. I prefer the outermost atom, and they work my way. So then I put in my 3 pair, 1, 2, and 3. So then I do an inventory, double check to make sure that I've not violated my 5 pair quota that I have to work with. I go back and check. I got 1, 2, 3, 4, 5 lines, each represent a pair. So I still got 5 pair. And I do that as you go through the process. You check after you've done a 1 step, go back and check to make sure you're still maintaining the number of electrons that you started off with, because you can very easily add more electrons by mistake, and you can also very easily not add enough electrons. Okay, so at every step you do an inventory, you check. All right, now the next step is to check the octet. As we stated with hydrogen, hydrogen's good, so it's happy. It's got 1 pair there that is being shared with carbon and the hydrogen. Okay, remember, these are covalent compounds, so that line represents a shared pair of electrons. We're going to talk down the road about equal sharing and unequal sharing, but right now it's simply they're being shared. So that bond between hydrogen and carbon is counted toward each one. So there's 2 electrons that count toward hydrogen, 2 electrons that count toward carbon. Okay, nitrogen has 8 electrons around. 1 of them is shared with the carbon, and then there's 3 pair around nitrogen. So with respect to nitrogen, nitrogen's doing okay. It's got the octet. We're looking now for the octet. But carbon here, if we count the number of bonds around carbon, we see there we got 2 pairs, 1 shared with the hydrogen, 1 shared with the nitrogen. So that's a total of 4 electrons. We got 4 electrons around carbon, we got 2 around hydrogen, and we got 8 electrons on nitrogen. So nitrogen is okay, hydrogen is okay, but carbon is not. Now here's where we're going to kind of take from Peter and share with Paul. Okay, we're going to take electrons from another atom, and we're going to create a new bond to share with the other atom. So that means, for example, since carbon is deficient, we're going to take a pair from nitrogen, and we're just going to put it in there and create a double bond. So let's do that. So we're going to do carbon double bonded to nitrogen, and then we still have those 2 lone pair on the nitrogen. So now we go check again. Again, do we have a total of 5? Yes, 1, 2, 3, 4, 5 pair. We're still good on that, okay? Now we go back, check the octet. Nitrogen still maintains the octet, it's good to go. Hydrogen still okay with the duet. Problem now is that carbon has only 6. It picked up 2 electrons, but there's only 6. So what we do is we take another pair on the nitrogen, I'm drawing the line here, and create a triple bond. So now we got carbon, triple bonded to nitrogen, and then I'm gonna go ahead and just put the 2 dots there for that single line. It's a line would have been fine, but I'm just gonna demonstrate at this point. And then the hydrogen, okay? Now, go back and do your inventory, make sure you're still maintaining the 5 pair. I got 3, a triple bond, 3 of them, okay? A single bond with the hydrogen, and then the lone pair on the nitrogen. So that is 5 pair of electrons. I put double dots here, but no problem with making a line like that, okay? So we maintain the 5 pair throughout, okay? Now we check the octet. Okay, nitrogen is still good, okay? We have 1 lone pair on the nitrogen, and then 3 pair being shared with the carbon, so nitrogen's good. Hydrogen is always is good to go. Carbon now, where it had 6, now has 8, okay? Has 1 pair that is shared with the hydrogen, and then 6 pair that are being shared with the nitrogen. So the octet has been fulfilled for carbon. So everybody now is in a stable state with respect to valence electrons. And that is our structure. Now, from there, we do the ABE general formula, okay, where A represents the central atom, okay, B represents what is bonded to the central atom, X, subscript X represents the number of atoms that are bonded to the central atom, which could be 1, which could be 2, at the maximum it could be 4, okay? And then E, this is important, E, I'm going to call that Y, subscript Y, represents the number of lone pair of electrons on the central atom, okay? All right, I'm going to repeat that because that's important. E represents the number of lone pair of electrons on the central atom, not on the atoms that are attached to the central atom. In this case, nitrogen has a lone pair. We're not concerned about that, okay? So let's figure out, everybody's going to have an A all the time. A is the central atom, that's it, Wayne. B represents who is the atoms bonded to the central atom. They could be the same or they could be different. We got a nitrogen and a hydrogen, so we got a subscript 2, okay? E, we don't have because there are no lone pair on the central atom or unbonded pair. Lone pairs are just by themselves and they're bonded, they're not doing anything, they're just sitting there. So on carbon right now, there are no lone pairs. Everybody is bonded, okay? So we don't have any. So that AB2 is our general formula. With that information, now we have the structure here, okay, with the triple bond. Now we go to the where do you go? Shapes table. Okay, from the shapes table, we look for the AB2. Okay, so we have here's a generic formula, ABE, that the first column, second column gives us the geometry, third column gives us the name of that shape, and then the particular bond angle between what is bonded to the central atom. So we look for AB2, here it is, okay? And this is the geometry. This could be carbon in the center, and then we got nitrogen there, and then we got the hydrogen right there. And then the bond between the nitrogen and hydrogen, the nitrogen and the hydrogen is 180 degrees, okay? Bond angle. That has a specific name. This particular geometry is called linear, and then we have the bond angle listed, okay? And so from the valence electrons, knowing who the central atom is, we figure out a structure. From that structure, we determine the general formula or the generic formula ABE, come to the shapes table, find that general formula that gives us the geometry, that gives us the name of that shape, name of that geometry, and plus the bond angle. Okay. And this is what we just calculated. All right. Now let's do the next one. Obviously, we're not talking about the name of these compounds. That's not important at this time. All you need to know is be able to identify the central atom and what is bonded to the central. All right. But I'll tell you what these species are. This is a hydrocarbon, specifically a fluorinated hydrocarbon. All right. So we got one carbon, okay, which the valence electrons again is 4. It's in group 4. One hydrogen again, one valence electrons. Now we have 3 fluorides. 3 fluorides belong in, fluorides are in group 7, right? 7. So every fluoride brings 7 valence electrons, and there are 3 of them. So we got a total of 21 valence electrons coming from the fluorides. Okay. Now we tally it up. We got 4, 5, 6, 26 total valence electrons to work with, which is divisible by 2, which tells me I got 13 pair of electrons, valence electrons to work with. Okay. We don't care about the core electrons because nothing's happening with the core electrons. All the bonding interaction is occurring with the outermost shell. Okay. The outermost shell, which is the outermost valence electron. All right. So now we got 13 pair to work with. That is our number that we have to stick with. We got carbon as a central atom, 1 hydrogen, and 3 fluorides around it. So we can very quickly generate that particular structure. We got 1 hydrogen, and then quickly add 3 fluorides around it. And that took care of 4 bonds, 4 pairs, I should say, right? And so -4 from the 13 says we got 9 pair left to work with. Okay. So this is where you got to think about this situation now, and remember duet octet. Hydrogen, as I stated, always 100% of the time has 1 bond to it. That's it. No more electrons can go. So hydrogen's good to go. Okay. Carbon, let's look at carbon. It's got 4 bonds around it. Each one has 2 electrons. So there are 8 electrons around carbon in this particular structure. Okay. So I can't add any more to that. Here's a key point. You won't see 10 valence electrons, nor you would see 6 valence electrons. The only place you're always going to have either 2 for hydrogen or 8 for everybody else. Okay. If you add a pair of electrons to carbon, then it's incorrect. That says the structure's not correct. From an energy perspective, it cannot deal with it. Okay. Doesn't mean it can't happen. It just, if it does, it's going to get rid of them right away. Okay. So you got to maintain that 8. So there's no place else. I can't put them on carbon. I can't put them on hydrogen. So the most logical place to put the 9 pair, obviously, is on the fluorides, right? So let's do that. So I got 9 to work with. I go 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay. Now go back and check to make sure you still maintain the 13 pair. You just did the 9, so that 9 pair is taken care of. You had 9 around the fluorides, 9, 10, 11, 12, 13 around the carbons. Okay, so you have maintained the 13 pair or 26 valence electrons. Okay. Now you might say, well, how come you use a double line? Well, this is why. As if I use the double dots, I should say, all right, that's going to be a lot of double dots. All right, you see right here, And then I got double dots around the fluorides, and you see you can easily end up losing some dots if you're not careful. And so these two structures with the double dots, with the dots or the bar or the line is good. I'll accept each one. But if you use the dots, make sure you have the correct number of dots. There should be 26 dots there to represent the individual valence electrons, or 13 lines to represent the pair. Okay. All right. Now we need to determine the general formula. All right. Well, we got A as always, and then we got B. B is 4. There are 4 species around the central atom. Okay. 3 hydrogens and one hydrogen and 3 fluorides. So that is our general formula. We go to the shapes table, look for AB4, which is right here. Okay. That is the particular shape we have here. This is carbon. There's one of the hydrogens, and then the 3 fluorides around it. Okay. There's the line that represents the bond. Remember that in this bond, there's 2 electrons. Okay. There's 8 electrons all around carbon and 2 of them in each bond. They're repelling each other. So those 4 pairs are going to repel each other. And so what's happening is the repulsion is such that they're going to adjust themselves to maximize the distance from each other. And that is the shape that they end up being. And then we call that tetrahedron. And the bond angle between the species, between the fluorides, is 109.5. That's a typical structure out in nature and throughout. That's 109.5. That's a typical kind of our benchmark with respect to bond angle. And then there's deviations from that. Okay. All right. Now, a key point about this aspect is if we look at the shape. So we got, before I proceed, that's our general shape. That's tetrahedron, then 109.5. Electrons play a big role in the way things structures occur. If you notice that this particular shape, general formula AB3E, very similar to the AB4, with the difference is there is a lone pair on the central atom. Okay, there's a lone pair in the central atom, and when that occurs, that's what those 2 dots here represent. They're a lone pair in the central atom. Those 2 electrons are not bonded to anything, and they tend to repel each other, okay, because they're negative charge. Like charges repel. The result is it forces that bond angle where it was up here at 109.5. It forces that bond angle to be less than 109.5, simply because that lone pair is just taking up more space, and because of the repulsion. If there was a bond, something was bonded to the lone pair, then they would go back to this particular shape. And those electrons can have a big effect on the shape of the structure, which then has an effect on the properties of that particular compound. All right, so with that in mind, that is the structure that we come up with. Okay. Now, we just do an interesting one. The next one, carbon dioxide. Okay. Let me erase these others so we have some space. We're going to do this guy right here, carbon dioxide. So, as always, we tally up the valence electrons. We got carbon, which again brings in 4. We got 2 oxygens, right? Each oxygen brings in 6, so we have a total of 12 valence electrons, okay? Don't forget to multiply the valence electrons by the number of atoms that you have. So each oxygen brings in 6 because it's in group 6A, and there's 2 of them, so we got a total of 12. So we have a total 12 for oxygen, for a grand total of 16 valence electrons, right? That my number look okay? All right. So that being said, we have that is equal to 8 pairs. So check my math, make sure I'm doing my math correctly. All right. So carbon is underscore. So carbon is the central atom. So we can quickly write carbon, and then there's 2 oxygens that are bonded to the central atom. So we can very quickly draw 2 lines for each oxygen, and that takes care of 2 pairs. So that leaves me with 6 pairs left to work with. Now, where you put them, since we don't have to worry about hydrogens here, where you put them is totally up to you. Okay, you put them anywhere. But like I stated, I prefer to start on the outside just to keep track of everything and then work my way in at once the outside is full. So I got 6 here, and I go 1, 2, 3. Now I can't add any more to the left oxygen, okay, because there's a total of 8 electrons around it already, okay. And I can put it on the carbon if I want, but like I said, I prefer to stay in the outside atom. So I took care of 3 there for the oxygen on the left. So I got 3 left. So I just go to the other oxygen and put 3 there. Okay. And I took care of that. So I've accounted for all of my pair. Okay. So I go back and do an inventory to make sure you still have 8 pair, and double check. Yes, you do 6. For 6 around the oxygens, lone pair, and then the 2 that are being shared with the carbon. That's a total of 8. So I'm good to go. Okay. Now check the octet. The left oxygen has 8. That's good. The right oxygen has 8. So that's good. Carbon only has 4 around it. Okay. So this is where, keep it in mind, I cannot magically just grab them from the air and stick them in there. I got to work with that 8. Okay, so this is where I take from Peter and share with Paul. I use that analogy. So I'm going to take from oxygen and share with carbon. Okay, and carbon is missing, 4 electrons. So I can take 1 pair from the left oxygen and make a double bond there, and I can do the same on the other side. Okay, and so the result now is as follows. I create this double bonds on both sides of carbon. Okay, go back and do your inventory. Make sure you still got 8 valence electrons around the whole thing. I got 1, 2, 3, 4, 5, 6, 7, 8. That checks out. I didn't lose those valence electrons. I still got 8. Okay. Once I'm done with that, check the octet. Oxygen still has 8. Okay, now it has 4 shared with the carbon as a double bond, and now 4 on the oxygen itself. The same is true with the oxygen on the left hand side. There are 4 electrons being shared with the carbon, and then 4 lone pair on the oxygen itself. Carbon now has 8 around it, being shared with both oxygens on the left and right, and so now we're good to go. That is the structure. All right, the formula structure that we put together, given this information now, and we're going to learn something interesting about this structure down the road here with respect to properties. All right, so our general formula will be A, B, 2. We don't have any lone pair in the central atom. We just have 2 atoms bonded to the central atom. And so it's going to be very similar to HCN. Okay, so let's go back into verify, and we're looking for AB2. There it is right here. Okay, here we got carbon there. Here's oxygen there, oxygen there. The bond angle between the 2 is 180 degrees, and its name for the shape is linear. Okay. All right. That's out, and there it is. All right, now finally, we're going to do the last one. Let me make some room here. All right, so now what we have is 1 nitrogen. Okay, the nitrogen is in group 5, so we got 5 valence electrons. We have 3 hydrogens, each one bringing 1 valence electron, so we have a grand total of 8 valence electrons to work with, okay, or 4 pairs. Now, given the information, nitrogen is the central atom, so we can very quickly attach 3 hydrogens around it, okay, as so. So now we got 4 pairs, 3 pairs that we took care of, so we got 1 pair left to work with. Now, obviously, we cannot put it on the hydrogen. Hydrogen is maxed out with the its duet rule. However, nitrogen is not, it's only 6. So the only logical place to put that lone pair that we got left here is on the nitrogen, okay? And that takes care of the pair. So go back and check, we still got 4 pair, which is what we started off with. And we're good. General formula is A, obviously, and then B3, because there's 3 hydrogens here. Now, we do have a lone pair on the central atom, so now we have an E, okay? So our general formula is AB3E, because there is a lone pair on the central atom. So that takes us to the shapes table, and we look for AB3E, and here we go, right there. So this could be the nitrogens and then the 2 hydrogens around it. And its particular name, which we would have thought, initially that because it has a shape, we got 4 items, 4 moieties around the central atom, it would be tetrahedral. But because one of the moieties happens to be a lone pair of electrons that take up a lot more space, they cause that bond angle to shrink in. Okay, so that bond angle is much less than 109.5, and it has its own little name. It's called trigonopyramid. Okay, trigonopyramid. We will learn that we did H2O, which was this particular structure. Okay, right here, 2 lone pairs. It had an AB2E2, 2 lone pairs on the central atom, and we called that bent. And that bond angle is much, much less than 109.5. Those lone pairs, I can tell you right now, those lone pairs on the central atom have a big effect on what we call the polarity of the species, and things like, what makes it more soluble in water and then more soluble in say in non-aqueous systems, is it more soluble in oil or more soluble in water? And those lone pairs could have a big factor in determining that. Much more on that down the road. All right, that formula, by the way, is ammonia. So might as well get used to that, because that ammonia keeps popping up down the road there. Okay. All right. This is a rehash of what I did with the first one, HCN. Okay. And coming up with the same structure. So the key here is when you come up short with respect to fulfilling the octet, you do not magically just add electrons or remove them. Okay, you got to work with what you calculate. And if you end up with not enough, then go back and check your math. Maybe you added incorrectly, or, and it happens a lot, you have nitrogen, which is in group 5, but you mistakenly give it a group 6 valence electrons. Okay, so you've added an electron. So you have extras, you got no place to put it. Okay, or the other way around, you're working with nitrogen in group 5, but you mistakenly give it 4, thinking it's in group 4. So now you come up short with electrons. And so go back and check and make sure you got the correct group and the correct number of valence electrons and the correct total number of electrons from each atom. Sometimes we forget to do that. The last one we just did, I had 3 hydrogens. Sometimes students add just 1. And in reality, it should be 3 because there's 3 hydrogens. Okay. All right, which brings us to Lewis dot structure, to what we call the polyatomic ion. Well, let me refresh your memory as to what these are. Now, the on the periodic table on the far left, we have a table within the table called labeled polyatomic ions. Okay, I briefly mentioned these way back when. These are specific units. Okay, we keep them together. So, and they have their own very specific name. We don't change the name to that unit. And if you notice, these are ions. Okay, though they are covalently bonded species, they are ions, and therefore a lot of them are soluble in water. Okay, overall, that unit has an overall charge, even though they are covalently bonded. Okay, a lot of these come from what I mentioned earlier was when I said that one of the differences between ionic bonds and covalent bonds was that ionic bonds, when we place them in water, will dissociate. And I stated that covalent bonds, well, they don't do that. Okay, but I also stated that there's only one group of covalent bonds that do that, and those are acids. So a lot of these negative charge species come from acids that were covalently bonded compounds, but then when they reacted with other things, which we're going to learn about, they formed these ions. Okay, now the Lewis dot structure procedure process is the same that we've been doing. Okay, we tally up the valence electrons. Where it differs is depends on the ion that you have. If the ion is negative, we're going to either add or subtract to the tally of valence electrons. Okay, it doesn't mean we are subtracting or adding valence electrons. It means that these electrons, depending on the charge, are being tied up. Okay, and being tied up structurally and bonded to something, they have to be accounted for in a different manner. Okay, we have like a correction factor, basically, is what's going on. We have a correction factor. So we do the same 4 steps, but we take the charge into account. Okay, so if that charge of the polyatomic ion is negative, we have to correct for that tally of valence electrons. So we need to add a number to it. That number depends on the charge. If it's a negative 1, we add 1. Negative 2, we add 2. Negative 3, obviously we add 3, right? So the amount of what we add depends on the charge on the ion. If it's a positive charge ion, and if you look at that table, we're only going to be dealing with one of them. And what we do is we take away from the total number of valence electrons. That is the correction factor we have to do. Okay? So negative ions, we add a value. Positive ions, we subtract. And the magnitude that we subtract depends on the charge. Once we're done, we draw the structure. We're going to be told who the central atom is. We draw the structure like we normally would, okay? And then we put a bracket around the whole ion and put the charge on the top right side. Okay, let's try this. All right, so we have the ammonium ion. This is the ion right here. NH4, okay? NH4, erase here. And so what we do, make note of the charge of that ion. It is positive. Being positive, we have to subtract from our total tally of valence electrons, okay? And so we have 1 nitrogen, which is in group 5, and we have 4 hydrogens, which is in group 4. And so one giveaway that would be that if you add, these 2 numbers, you end up with 9, right? Well, here's the thing. You got 9, and as I stated, all these valence electrons should be divisible by 2. So the fact that you get an odd number should flag you to say, ooh, I did something wrong, okay? And maybe I need to go back and check. So here you go back and check. We go back to pressure memory and says this is a positive ion. So we have to subtract 1 from the total valence shell. So we have a total of 8 valence shells to work with, or 4 pairs, okay? Nitrogen is the central atom. So we can very quickly put nitrogen and then bond the 4 hydrogens around it. Okay. And erase this. No different than what we have been doing. Now what we do, we got 4 pair here, okay? Now we put a bracket, not the parentheses, but a bracket. And then in the top right corner, we put the charter for that ion. And that's how we present the Lewis dot structure for polyatomic ions. Now, can we determine a formula, a general formula for this? Yes, no different than we've done before. This will be AB4. A is the nitrogen, 4 atoms bonding around the central atom. So our general formula would be AB4. And we go to the shapes table like we've been doing, nothing different. And AB4 would be right here. There's nitrogen sitting there. Here are the 4 hydrogens bonded around the nitrogen. Here's the bracket that we put around it and the plus. And the species inside, the structure would be tetrahedral and 109.5, just like we've been doing for all the other compounds that we've done so far, okay? Yeah. All right. So that's what we kind of, don't forget the bracket. Okay. And like I said, we're going to probably, we're only, as far as cation polyatomic ions, the ammonium is probably the only one you're going to be working with. There's more negative anion polyatomic ions than that we'll work with than they are positive. Okay. So for example, let's try these. Now, obviously we don't know what they are, and that's okay. But what we're giving you here is a general formula with a charge. Okay. We got bromine, which here can act as a central atom, especially when it's bonded with oxygens around it. So we got bromine and 3 oxygens around it, okay, in this first example. And then we have the sulfur with 4 oxygens bonded around it with a -2 charge. And then we have this species here, which is very similar to what we did. Remember we did the HCN one? Well, what happens, this is called the cyanide, the negative charge, because what's happening here, we treat it with an acid and we remove that hydrogen and we put a negative charge in there. So this is an example of a polyatomic ion. And like I said, normally most of these have come from acids, organic, I wouldn't say covalent acids. All right, let me clear this up. So the step is as follows. We do what we've been doing, tally up the valence electrons. Bromines in group 7 valence electrons. There are 3 oxygens coming from group 6, each one, so that's a total of 18. This is a polyatomic ion. That's crucial. You gotta remember that. You're dealing with polyatomic ion and it's negative, so we're gonna add a correction factor, which is 1. Okay, so we tally it up and we end up with 26 valence electrons, or 13 pair. Now, once you do that and you got the pair that you're working with, well, very simple. The bromine's in the central atom, and then I can quickly write 3 oxygens around it. Okay, that took care of 3 pair, right? So I got 10 pair left to work with. All right, now what do I do? Well, as I stated before, I start with the outside atoms, fill those up, and then work my way in. I'm no different here. I got 10 pair to work with. I'm going to go start one of the oxygens for 1, 2, and 3. Okay, that took care of 3, and I got 7 more to work with. Okay, and then 1, 2, and 3 around another set. So I got 4 to work with, and then I take 3 more on the other oxygen. So now I got 1 pair left over. Okay, now I can't put them anywhere else because the oxygens have the octet full, but the bromine doesn't. There's only 6 remaining, so the only obvious place is to put them in the central atom. Okay, and that takes care of that 1 pair. So go back and check to make sure I still have 13. Okay, I got 6. Okay, 6, 9. 10, 11, 12, 13, 13 pair, which is consistent with the number that I had. Okay. Now, I put a bracket around the whole thing. And I'll have a cleaner picture here in a minute with a negative charge. Okay. And that will be what I present, this Lewis dot structure. And then the general formula, in case I'm asked information about this, is no different than we did before. We got A. Okay. B will be 3, and then E, we got an E here because there is a lone pair on the central atom. So our general formula will be AB3E, okay? And that we go to AB3E, which is that structure. So here we got the bromine in here, and then we got the 3 oxygens around, and then that lone pair on the bromine, and then we put that bracket around it and the negative charge. Its name is trigonopyramid, and its bond angle is much less than 109.5. Okay, no different than what we've been doing, except we put a bracket around the structure and then its respective charge. Okay. All right. The next one is called sulfate, but right now we don't have to worry about the names. We do what we've been doing. Sulfur is in group 6. There are 4 oxygens. Okay, so that's a total of 24. And then we add 2. Okay. Then that gives us a total of 32 valence electrons, or 16 pair. Okay, so now we can start. We got sulfur is the central atom, and then it is bonded to 4 oxygens. Okay. I know I'm going to have a bracket here, and I know I'm going to have a -2. Okay, so that took care of 4 pair. So I got 12 pair to work with. And obviously I cannot put them on the sulfur because that would violate the octet rule. So the only place to put them are around the oxygen. So I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, I took care of that. I still got 16 pair. I didn't lose any. I didn't add any inadvertently, and I'm good to go. Okay. So now the general formula, no different. A, B, 4. Okay, I got 4. So that would be, you can go back and check the shapes table. That should be tetrahedral. Okay, and bond angle 109.5. All right. And finally, the CN negative polyatomic ion, otherwise called cyanide. Okay, 4 for the carbon, 3 for, 5 for the nitrogen, and then we're going to add 1 because the negative charge. Okay, and so here we have a total of 10 pair, and the 5 pair, total of 10 valence electrons. And I'll let you go through the process, but you end up with, again, like we did the first one, triple bond between the two, and then a lone pair both on, excuse me 1 second. I had to sneeze. Oh, sorry. And so here is general formula. You can look it up, but you can tell there's only 2 atoms there. It's going to be linear. Okay. There's really no central atom here. It could be either nitrogen or the carbon. Yeah, because there's only 2. If there were 3 species like the HCN, then yes, you'd be central atom would be total. All right, so this is how we do Lewis dot structures for polyatomic ions. Okay, very the same as we've been doing before. We tally up the valence electrons. You're told who the central atom is. Okay, and where they differ, and then from that, with respect to the non-polyatomic ions, we take the general formula and determine the structure and so forth. Over here, we continue with the same process. At the end, we put a bracket around the formula we come up with and the charge in the top right corner. And then we can still use the general formula to determine its particular geometry. Okay. Don't forget to do the correction factor depending if it's positive or negative ion. Okay. I kind of touched on it a little bit here before, and I said about the lone pairs and how the lone pairs have an effect on the structure and so forth. You know, they can affect how things occur. And if they're lone pair, they're going to take up more space. So when they take up more space, it's going to cause the other moieties, the other atoms that are bonded to the central atom, to be squished in to each other, which then affects the overall properties of the molecule. Okay. And so basically they had this model called the valence shell electron pair repulsion, or the VSEPR acronym. Okay. That is just basically telling you electron pairs repel each other, and they're going to move away as far as possible. And in doing so, they're going to affect the bond angles of the whole molecule. Okay. All right. So we're going to basically go over the shades table, and I've introduced the general formula with ABE, where A is the central atom, B is the outer atoms, and E is the lone pair on the central atom. That's important. Lone pair on the central atom. All right. So when there are only 2 atoms, like these diatomics elements, or the cyanide we just did, the only structure, the only configuration I have is a linear configuration. Okay, there's really no bond angle to even deal with, because bond angles, you got to have at least two moieties bonded to a central atom. So no bond angle, they're just basically linear. Okay, an example, what we did was carbon dioxide is linear with 180 degrees. Now those double bonds forced it to have that particular configuration. Okay, because in creating that double bond on both sides, we have a bond angle here of 180 degrees. Okay. And so anything with general form of AB2 ends up with a linear configuration, bond angle 180 degrees. The AB3 is what we call a trigonal planar. Okay. All right, so we have a central atom, here in this case carbon, and then 3 moieties bonded around it. And so all the way around, it's like an equilateral triangle, so to speak. It's 120 degrees all the way around. All right, this particular species, for example, this is the formula for formaldehyde, by the way, FYI. A very small molecule, organic compound, but has been shown to cause cancer. Yeah. Anyway, we talked about the tetrahedral. This is the most common general in structure where we have A, the central moiety, and there's four species bonded, four atoms bonded to the central atom. And that bond angle is 109.5. And again, it attaches, it gives you that bond angle because, you know, these are electrons. There's two electrons here. See, all the way around, they're going to repel each other. And if we had magnets on the four corners here, you will find them that repel to each other. You'll find them just spread out, and that's the configuration they're going to get, the maximum configuration that they would obtain, so they can get away from the repulsion of the charge of the electrons. Okay, so tetrahedral, good example here is methane, a hydrocarbon. This tetrahedral configuration is found a lot in nature. Then we have what's called the ABE bent, okay, where this one is, you would think that, for example, we just did, here's a good example. We just did carbon dioxide, okay, where we had CO2. Okay, and here we got CO2, we got SO2. And what we think, okay, well, maybe because we just did CO2, maybe SO2 would have the same formula or same structure, and that's not the case, right? Why? Because sulfur is in a different group 6, than carbon is, and so it's going to bring more electrons to the table, so to speak, right? And sure enough, when it does that, it's got a lone pair sitting right there. And the result is, you would think like the previous example we did with this one, it would be 120 degrees all the way around. Well, unfortunately, because of the lone pair repelling each other, it causes this angle here to be much less than 120 degrees. So anyway, this has the, clear this up a little bit, the bent configuration, All right, then this is an example of ammonia. Anyway, this is sulfur dioxide, FYI, compared to carbon dioxide. This is sulfur dioxide. And then we just did the ammonia, and where we end up with a lone pair again on the central atom. We have the general formula of AB3E, which has the name trigonopyramid, and that bond angle is much less. This this would be where the lone pairs exist, causing this bond angle here between the hydrogens to be much less than 109.5. And then we got a good example here is water, where we got AB2E2, and here we got two lone pairs. I'm kind of drawing like globes here, and they're going to repel each other quite a bit, causing this bond angle to be much, much less than 109.5. It should be like a triple less than symbol, okay? That results in making water what we call very, very polar, okay? We're going to learn about polarity of these compounds, and we're going to have polar and we're going to have non-polar. And the best way to think of these, not the best way, but one way to think of these is polar is compounds and molecules that have water-like properties, okay? So we know that like, we use the adage of like dissolves like. So if a molecule has properties of water, they're going to dissolve in each other. We also know that oil and water don't mix, right? Oil is what we call non-polar, all right? And water is a good example of polar. And these compounds all we're going to end up to determine where to classify them on their quote polarity, depending on their bonds and their lone pairs and everything. And if it's polar, it would be more likely dissolvable in water than in oil. Okay. So I use the example because growing up with 5 sisters, that during the night, they had all kinds of stuff on their face to get that makeup on. And you guys, those of you who use the makeup can verify this. There's some makeup that, you know, you can wash off with water, and then there's some makeup that you need, like, you know, WD-40 to take off, because you need an oil-based cleanser to get that makeup off, you know, because I'm told there's some makeup that's like hurricane proof, you know, you can get it with water, but you still be looking good, no running and so forth. And that's a difference in polarity, okay? That oil, that makeup that sticks with all the water around is a lot more non-polar character, therefore will not dissolve as readily. But much more on that down the road here. But all that's related to these lone pair of electrons. So I can tell you right now that whenever you come up with a molecule that has a lone pair on the central atom, without question, you can classify it as a polar molecule. Okay, polar molecule. Whenever you end up with a lone pair. Right, so to summarize all this, given any covalent compound or polyatomic ion, you should be able to draw the Lewis dot structure, and then from that information determine the general formula, and using the shapes table, determine the shape and the name of the shape and the bond angles. Okay, so you may want to try as an exercise these compounds here and see how you do. Try these on your own, and then any question about it, we can, you know, bring them to class and we can go figure it out. Okay. All right. Let's continue here. Oh. Okay. Which brings us, I just mentioned, introduced the term polarity. Okay. And to determine the polarity of the molecule, we have to look at the polarity of the bond. Okay. The covalent bond specifically. Now, I also mentioned that when there is a bond between atoms, there's going to be either a equal sharing of those electrons or an unequal sharing. When those bonds are equally shared, okay, we classify that as a non-polar bond. Okay. In other words, non-polar meaning there's no pole. The Earth is polar. Think about it. We got a North Pole and a South Pole. Okay. The battery that runs your electronics is polar. We got a positive and a negative. Right. So what's going to happen, if you give us some thought, is when we get into a polar bond, there's going to be an area that's going to have a little bit of a pole, not a full charge like ionic compounds, but it's going to have a little bit of a charge because it's pulling all the electron density onto itself. And that is related to the electronegativity that we talked about way back a while back, about the electronegativity, not the ionization energy, but the electronegativity, which was the measure of an atom's affinity for electrons when it's bonded to something. Okay, so it's everything's, you know, kind of trying to put everything together here. So when there's equal sharing in a bond, we call it a nonpolar bond. Now, the best way I think to look at it is just in generic terms and say, okay, if I have A is some element bonded to A, which is the same element, then we're going to end up with a nonpolar bond. Why is that? Because the electronegativity of each one is the same. There's an equal pull. It's like it's a tug of war. That bond, there's a tug of war going on between the electrons. And in this case, it's an equal tug of war. It's like having 200 pounders on the rope and doing a tug of war. Basically, it's not going anywhere. Okay, it's equal pull. Now, if we change that A and make another element, put in another element, which I'm going to denote as B, automatically, I can't overemphasize this, automatically, I have a polar bond. Now you might ask, why is that? Because the electronegativity between A and B is always going to be different. And once that's different, you have a polar bond because one of these guys is going to pull the electrons onto itself. The only exception, and this is long-term memory, the carbon-hydrogen bond, okay? Even though they're two different atoms, the electronegativity of the carbon and hydrogen is essentially the same. Therefore, anytime you see a carbon-hydrogen bond, it is a non-polar bond. All the other examples, the diatomics, non-polar bond, because diatomics, the two atoms are the same, okay? So that means that anytime there's a different species bonded to each other, I got a polar bond. Now, which direction that affinity of electrons goes to depends on the electronegativity of the atoms. And remember the periodic table? We have fluorine in the corner there. Fluorine is the most electronegative element there is. And the trend was from left to right, electronegativity goes up, bottom to top, electronegativity goes up. We use fluorine as our reference point, okay? And if we ever have two elements that are not fluorine, and we want to know which direction the electron pull goes, then we find its position relative to fluorine. So if the bond is HF, for example, no question, fluorine is most electronegative. Fluorine is going to pull its electrons toward it. But if it's, say, carbon-nitrogen bond, you got to find its position relative to fluorine. You'll see that nitrogen is closer to fluorine. Therefore, nitrogen has a higher electronegativity. You don't have to memorize its individual electronegativity. It's not necessary. You want to, go ahead. Every element has electronegativity value, except the noble gases, they all have zero, right? But nitrogen has higher electronegativity, and so what happens is it's going to pull electrons onto itself. And so we end up with a polar bond because nitrogen is pulling the electrons. But let's just say that in this example, nitrogen's over here, carbon's over here. Because it's pulling the electron density away from the carbon, it's going to pull the electron density on carbon gets less. The result is we end up with this symbol called partial. We end up with a partial positive on the carbon side and a partial negative on the nitrogen side because the nitrogens are pulling the negative electrons toward itself. So more electron density in that area, hence a partial negative. Not a full-fledged positive and negative like the ionic compounds, but a partial. The result is we have a polar bond. A polar bond is anything that, like the Earth, has a North Pole and a South Pole. And we have a polar bond when we're dealing with polar molecules. Oh, we have a polar bond when the two atoms are different. Okay, automatically, the two atoms that are bonded, automatically you have a polar bond, except carbon-hydrogen, okay? It's the only exception. When you've got one exception to worry about, that means that everything else always polar. Now, to determine which direction the polarity goes, you determine which has a higher electronegativity, okay? All right, so that is the polar bond and non-polar bond. And that, once we identify the bond, whether it's polar or non-polar, then we can go on and take that information along with the structure information we just come up with and determine whether the molecule overall is polar or non-polar. Okay, because in general, when all the bonds in your molecule are non-polar bonds, then the whole molecule is non-polar. Okay. In general, when all your bonds are polar, you end up with a polar bond, except under certain conditions. And we're going to talk about that. Okay. because it is possible to have polar bonds and end up with a nonpolar molecule. Classic example is carbon dioxide. We'll explain, we'll get through that. We'll eventually finish this chapter. It seems like it's taking a little bit longer. So refresh your memory about electronegativity, okay? And that is the affinity for electrons repelled onto itself, the atom. And as I stated, fluorine is the most electronegative element, okay? And noble gases obviously don't have that. So the general trend is a refractor. Left to right goes up. Fluorine is right here. And so that's our benchmark. That's our reference point. Okay. This. All right. So nonpolar covalent bonds, all of the 7 diatomic elements are nonpolar. Why? Because the 2 species are the same atoms. Okay, they're both the same. The other exception is the carbon hydrogen. That's also nonpolar. Why? Because the electronegativity between the difference between carbon and hydrogen is minimal. They're treated as the same electronegativity value. Therefore, it is a nonpolar bond. Okay. Yeah. Because a lot of hydrocarbons out there, a lot of oils, for example, are carbon hydrogen bonds, and a lot of them are nonpolar. They don't mix well with water. Okay. All right. So where am I? Got a couple minutes. Polar covalent bonds, and most covalent bonds are between 2 different nonmetals. Notice again, that's what I use a generic example for nonpolar species. I think of them as A and A, bonded to A and A. Okay, and that includes carbon hydrogen, even though they're different. And so when you see it's an example where you got A plus B bonded to B, then automatically think polar bonds, automatically, because those 2 different elements will have different electronegativity values, which results that one of them is going to be pulling the electrons onto itself with much greater force than the other, resulting in a polar bond. Okay. And things like carbon, oxygen, hydrogen chloride, sulfur fluoride, silicon nitrogen, anything that's 2 different elements bonded together, non-metal. Okay. Now the silicon, which is a metalloid, it can make bonds too. And we won't deal with a lot of that, but because they're metalloids, they have properties of both ionic and non-ionic properties. So if it's bonded to a non-metal, then think of it as the whole molecule as a covalent bond. Okay, unless you see it bonded to a metal, then obviously you think of it as an ionic bond. So all of these are polar covalent bonds, and what we do is to indicate which direction it goes, we use this polar arrow, which has a little plus end on the left side on one end, and the arrow. The arrow represents where the negative part goes. Okay, so in this carbon fluoride example, carbon fluoride bond, fluoride is the most electronegative species out there. So in that bond, it's going to pull electrons onto itself with much greater force than carbon. The result is the electron density around fluoride is much greater. And so if I kind of draw it somewhat, and I'm going to, next time around, we're going to use some of the simulations. So this is kind of exaggerating it a little bit, but you can see normally if we were looking at hydrogen and hydrogen bonded, then the electron density cloud could dimensionally be equally distributed. But when one of them has a higher electronegativity, it's going to pull electrons onto itself much greater force. Fluoride is going to do that, resulting in a partial, this is the lowercase k, I think it's delta, partial negative on the fluoride, and a partial positive. That aspect is extremely important in organic chemistry because that allows us as chemists to be able to synthesize and make compounds. Without that polarity involved, it'll be very challenging to make whole new compounds because that's the driving force for a lot of chemical reactions. All right. So carbon fluoride, the arrow goes from left to right. Okay. Oxygen, hydrogen, in this example, the arrow will go from right to left. Now, if it's written with hydrogen on the left, obviously the arrow goes in the opposite direction. Okay. The arrow, that polar arrow has that positive tail, and then the arrow points toward the negative. And then the phosphorus chloride, well, we look at their position, both in the case of the oxygen and the hydrogen, and the phosphorus and the chloride, look at their position relative to chloride, and we determine that chloride is a lot more electronegative, so therefore it's going to have the partial negative side, whereas leaving the partial positive side on the phosphorus. Okay. Oh, got a question. Oh, okay. All right. I went over. Sorry, guys. I got a little carried away here. We're on slide 37. Let me mark this before. All right. We'll be done with this on Tuesday and then jump into the next chapter is like 24, 25 slides. And it's very, very quick. So I'm on 37. All right. Let me clear my